So in this video, we're going to look at problems 1 and 2 from the Chapter 3, Part 2 homework. So here we have a plate. It's acted upon by two forces. We're told that the magnitude of these two forces is identical. So right away, hopefully after watching the last video, the concept of a couple is clicking in your head. In addition, we note that the direction of this force that's applied at point A is defined by a 60-degree inclination in the counterclockwise direction from the positive vertical, and the direction of the force at point C is defined by a 60-degree inclination from the negative vertical. And what that means is that if I were to extend the lines of action of these two forces, they are in fact parallel. And hopefully by observation, you see that they're directed with different senses along those parallel lines of action. This is going in the upper left, this is going towards the bottom right. And hopefully you remember that those are the three definitions of an actual force couple system. Equal magnitude, parallel lines of action, opposite sense along those lines. So we know that what's going to happen in that situation is the resulting tendency to induce motion of that pair of forces is going to be purely rotational, because basically, if you think about it, the translational tendencies are canceling each other out. So all that this is going to tend to do is to actually rotate this plate. And hopefully, if you have a piece of paper in front of you, you can kind of demonstrate this, pulled up at the bottom corner and then pulled down at the other corner. And notice that you're going to get rotation. And hopefully, if you kind of hold it in front of you and look like that, you see that the axis that actually comes out of the plane, the rotation is in the clockwise direction. And if we define this as positive x, this is positive y, curled to positive z, hopefully everyone sees that that kind of clockwise rotation is about the z-axis. And particularly, we're going to denote it with a negative sign. I don't want to go into that in too much detail. I'll probably do it in one of the latter videos that deals in 3 dimensions. But just remember, for coplanar force systems, the rotation is always about an axis that comes out of the plane. So it's easier to just describe it in terms of clockwise rotation and counterclockwise rotation. And hopefully you see this pair of forces is going to rotate in the clockwise direction in the plane. So whenever you have a couple pair, we know that in order to compute the moment, we simply need to take the magnitude of the forces and multiply by the perpendicular distance between the two lines of action. And what your book is trying to do to probably get you to get this question wrong is to guess that the perpendicular distance between the two lines of action is simply the diagonal from A to C. But if you notice, this is a square plate, 200 millimeters or 0.2 meters wide and 0.2 meters high. So if you draw a line from A to C, that's going to be at a 45-degree angle. And in order to be perpendicular to a line that's formed by an inclination of 60 degrees from the vertical, you have to have a line that's drawn at 60 degrees from the horizontal. What I mean by that, I'll show you down here in my actual drawing. If we're trying to draw something that's perpendicular to these two lines, it needs to be aligned 60 degrees from the horizontal. And that is the distance that we want. The line that's along a 60-degree incline from the horizontal that goes to these two lines of action. And the easiest way to compute it is to view it as the sum of two different distances. So this entire perpendicular distance, d perpendicular, which is from one line to the other, I'm breaking it up into D1 and D2. And the way that I'm doing that is kind of at the halfway point, I'm drawing a line that's parallel to the two lines of actions of the forces. And what that is going to allow me to do, since it's parallel to those two lines, and D perpendicular is perpendicular to those lines, when I drop that, it's going to form a 90-degree angle. So I'm going to be able to use right triangle trigonometry. The other cool thing that is neat is I need these two base lengths. And if you notice, the actual side length opposite of the 90-degree angle which of course would be the hypotenuse in these right triangles, is also a side length of the plate that I already know. So I just need to compute D1 and D2. I know that in this little right triangle, the hypotenuse is 0.2. In this right triangle, it's 0.2 as well. So if I want to get this distance of the base, knowing that this angle is 60 and this angle is 60, and hopefully you can convince yourself of that, this has to be 60 degrees in order to be perpendicular to the two lines. This is 60 degrees because that line is actually parallel to these two lines of action. So here, if I know AB, I know this angle is 60 degrees. The base length that I need is going to be the hypotenuse, 0.2 times cosine of 60, because it's adjacent, versus in this problem, here is the hypotenuse, and notice that D2, the actual side length that we need, is opposite of the 60-degree angle. So that's where this weird thing is coming from. D perpendicular equals D1 plus D2. D1 is AB cos 60. That is this portion of the line right here. D2 is BC cos I should say sine of 60. I will correct that and rescan that. It's going to be a pain because I'll have to do the whole thing over again. I had it correct over here. But when you add those two things together, you get 0.2 times cos 60 plus sine 60. And then, of course, we already know the magnitude of the force. So simply multiply that magnitude of the force times the perpendicular distance, and you get 17.4854 newtons times meters. That is just the magnitude of this couple vector. In order to fully describe it, we need the direction as well. And since it's a two-dimensional coplanar problem, we can just say that it's that magnitude of torque in the actual clockwise direction. So for the second portion of this, we're actually asked to do it by decomposing the two forces into x and y components. We can easily break these two forces. If you look at the original problem, in an x component for the force that's down here today, that's going to be going in the negative direction, and a y component that's going to go in the positive y direction. I should have said negative x and positive y. Key thing to realize is relative to the 60-degree angle, the y component is actually adjacent. So you're going to get that by taking magnitude of f times the actual cosine of 60, versus the x component is actually opposite of that 60-degree angle. So in solving this problem, the first thing you want to do is kind of note that geometry that we just described there. And then note that in both cases, the perpendicular distances now are going to be the dimensions of the plate, because the actual y components of those vectors, if you extend the lines of action as I have here, you see that the perpendicular distance is just going to be a horizontal line, which is just the dimension of the width of the plate. In a similar fashion, if you do that for the two x components, notice that the perpendicular distance is just a vertical line that corresponds to the height of the plate. So in order to compute the total moment of that force by breaking it into components, you have to ask yourself, hey, in which directions do the x components tend to induce rotation? So if you take a plate in front of you, or a paper, and you pull it to the right at the top and the left at the bottom, hopefully you see that's going to be clockwise. And then if you do a similar thing, pull it up here and down here, both of those force couple pairs are going to induce clockwise rotation. So that means they effectively add. Well, you could say, well, clockwise is negative, so I'm going to make them both negative, and I'm going to add the negatives. That's fine too. But the key thing is they constructively interfere. So I just chose to add them both, and then just to note that the net rotation will be in the clockwise direction. I wrote it in this weird way just to show you that this is the same formulation of the problem that we got on the previous page. This is the magnitude of the force. So what we must be multiplying by is the perpendicular distance. And that's exactly what we did from a geometrical point of view here. We got this quantity and showed that it was the perpendicular distance. So that is a problem you can do in either way. It depends if you're more geometrically inclined or kind of more linear algebraically inclined, but of course you get the same answer regardless of your approach.